Welcome back, coaches. So what we're going to do today is go a little bit deeper into uh, training athletes and why the means behind training athletes and the methods that we choose, why they work, and what it is that we can do with athletes to take them to the next level of performance, not necessarily in sports skill, that's up to them, but in performance from a motor potential standpoint. So what can they actually do as an organism? So let's get into it. So the first thing is, when you look at any athlete, especially higher quality ones that you're trying to make even better, is you have to determine what are the aspects that make them good. Are they very elastic? Are they fast? Are they really strong? Are they very powerful? Is it their size of their body? Like, are they built really well for their sport if it requires size? So you got to determine that. And a big reason is that a lot of coaches will say, "Hey, we don't need to work on that. Strong suits are always strong suits." I agree, but it doesn't mean that you don't increase it further. If it's the quality that makes them good, well, then it might also be the quality that makes them great or untouchable if you can improve it even a little bit. So what do I work on first? Well, find out who you're looking at, find out the sport they play, watch them play, and then try to do some testing. So relevant tests with athletics a lot of times are going to have to do with speed, power, and strength. So if we want a really good one, that's going to encompass all of those things, it's going to be the reactive strength index. So a big thing is this helps you understand elasticity in the way that it's going to be used in sports. So the reactive strength index is basically your jump height divided by your ground contact time. And this is going to tell us a number of things. So there's a couple ways to get a high RSI. You can either jump high with a relatively long ground contact time, and I say relatively long because we're still talking about short ground contact times, or you can jump very quickly off the floor. You can have a really fast ground contact and still a moderate jump height and have a high RSI as well. But the cool thing is that visually you can see what that is, and you'll have a readout of, all right, the ground contact time was X, but their jump height was this, and then all right, the ground contact time was this and their jump height was only this. So it tells you, all right, exactly what you're dealing with. It's an easy test, it's easy to calculate, we love it. The bilateral jump height deficit. So this is a really cool way to determine if who is standing in front of you is velocity based or strength based. So what we do is we have an athlete do a single leg jump on each leg, and then we add it up. All right. Now this isn't a foolproof method, but it gives you a window. You add it up, and then you have them do a 2-leg jump of the same type. So either from a static start or counter movement, and then you compare that with the sum of the 2 single leg jumps. And the greater the deficit, the less velocity based that athlete is. And that's because when you have 2 legs going at the same time, the extension velocity of the limbs and the speed of the overall movement will be higher, and they should be able to produce a lot more force that particular way and result in a higher jump. But if they can't produce a lot of force in a really short period of time at that high velocity, then the jump is not going to be nearly as high as the sum of those 2 single leg jumps. So again, not foolproof, but it is it's again easy to see. Bilateral deficit findings. So the distinction was made here by considering the purely theoretical situation in which each single lower limb presented the same dynamic mechanical capabilities in unilateral and bilateral action, and in turn the same force-velocity relation. Assuming that no neural capability alterations occur between unilateral and bilateral conditions. Even in this specific theoretical situation, the force each limb could produce during maximal push would be lower during bilateral than unilateral action because of the higher extension velocity. So you can kind of see, look, if they can produce X amount of force on one leg when they jump on one leg, but they can't, neither limb produces nearly the same amount of force when they're working in unison, that they're just not as good at producing that amount of force at those higher velocities. If you were lucky enough to have it, things like the dynamic strength index are really amazing tests. Some people would argue that pulling against a fixed object while applying that amount of force is very compressive. For the most part, if you can get in a great position, I think it's very safe. But you need a force plate. So again, if you're lucky enough to have a force plate, you can do a maximum peak force mid-thigh isometric pull. So you would get a barbell underneath the pins, position yourself very close to it, preferably with straps, so that grip is not a limiting factor, and then apply force for up to 4 or 5 seconds and see what the maximum number it is that you can get. Then you can go and you can do the same thing on the force plate with the counter movement jump, and all you're going to do at that point is compare the peak isometric force in the counter movement jump with the peak isometric force the peak force in the pull. So you're basically looking at, look, what can they do absolutely in the pin pull, and then you're looking at what can they do in the context of that short time period with the counter movement jump. So we like that quite a bit. Obviously, again, really easy, not a really difficult thing to determine. So this is a really important table to look at. So this is just the phase of a plyometric action, which is what we see most often in sports. So whether or not it's a jump, it's going to be a plyometric action. Very few things start without any kind of counter movement or without energy before someone goes to move. So semi-plyometric or plyometric action. So we have the initial momentum phase. So we're moving, and then the first kind of action where we're going to start to apply force into the ground is going to be our eccentric contraction, and then we'll be lengthening. So we are yielding, but we are still applying force actively. This is actually a really important part of the force production equation. People will say the force that you can absorb. So you're actually producing force eccentrically to isometrically. You're not absorbing force. Your body is experiencing forces on it, and you are reflexively ratcheting up the tension until you can meet it, or not meet it if it exceeds certain reflex thresholds. And then we get into the explosive isometric. So this coupling time at the very bottom is going to be a centerpiece and a focal point of our talk today. This is the whole thing is the movement and the ground contact time is all going to be very centric around this coupling time, and that's why we care so much about this table. Explosive isometrics, firing really, really hard and then actually getting to a dead stop. And that's where we see our series elastic components come in, and then they start to contribute to that concentric contraction. So that's the whole rep. So we want to train that with context. So we look at, all right, what quality is it that we're trying to develop? Ultimately, with a lot of exercises, it's going to be the coupling time, and it's going to be the time between switching between eccentric getting to concentric action. So a lot of our things that we do when we're trying to change direction is more centric towards the actual change of direction than it is the takeoff out of the change of direction. It doesn't mean that that's not important. It's just that when we're training it in isolation, it is what it is. uh, when you train a lot of those things, it's very important that you are clear with your context so that everyone kind of knows what you're working on. Otherwise, it can be muddy water and you can still get a lot out of it. But if we're talking about making good ones great, then you are going to have to get specific. We're beyond that initial phase where everything works. Train any exercise that's plyometric. So all along the plyometric spectrum, we have that that kind of repetition or plyometric structure, just like that, intact. So it's all, when it comes to carryover, almost everything on the spectrum carries over. So that's why I tell you, everything plyometric is pretty good to go. It should have some kind of ground contact time where you're looking to either minimize it or get the appropriate ground contact time for the type of exercise that you're doing. And if there's no ground contact time involved, having some kind of plyometric action, which is basically just employing the stretch shortening cycle, is important as well, right? Yeah, there are things with isometrics and stuff like that are important, but really the explosive variety is the most applicable. Some of the slow stuff is nice in theory, but is really difficult to actually demonstrate an effect on sports. Velocity specific, so this goes along with the ground contact time. So there's going to be a specific speed that we know things are happening, and a specific speed window where we need to see those things happen. So we're going to be velocity specific. It's really nice, especially with barbell work, when we know that certain qualities are trained at certain velocities. It's a give or a take in both directions, and also very individual. Anything with stretch shortening cycle involvement is going to probably work okay, as long as it's close to what they may do, or it's appropriate in terms of tension or length on tissues. Impulsive loading is maybe one of the best ways to train athletes when it comes to keeping the context clear and making sure that the motor structure of the activity that you're looking to affect will be intact. So impulsive loading is basically moving around someone's, either manipulating their mass or their momentum, and then the closer you get to being specific, the mass is going to be pretty constant. So turning the system on and off, that nice kind of like, a lot of times with weight training exercises, there's so much static work, either posturally or on various tissues because you're standing still with external load. When we can use impulsive loading, things can naturally contract and relax at the speeds which we want them to, and also we can work on that speed. Neuromechanical importance. This is the closest interplay that we can really have with sports from a neuromechanical standpoint. So it's important to get pretty close. The skill co-contractor, this is going to go back up to the same thing as like, look, these are in the proper sequence that we would want to see them. And when it comes to intermuscular coordination efforts and specific strength training means, it's a pretty big deal to use more impulsive loading methods rather than going into the weight room. And then the last one is going to be, it's going to bridge the gap between strength training and kind of the intramuscular coordination stuff that we work on in the weight room and the co-contraction habits that we want to see on the field of play. So again, impulsive loading, it would be, taking someone and having them do straight leg bounds at a certain speed, or having them do changes of direction, moving from 7 yards out versus 5 yards out, because we know the momentum that they'll be able to build going into the change of direction will be greater. Therefore, the forces they experience and then reflexively produce in the change of direction will also be greater. And if we can get the coupling time down and we can shorten the interaction, to do that, then we've really made like something that's usable and that we can say we're actually affecting them positively. Muscular traction effort. So muscular traction effort is really what helps us stop and really helps us utilize our series elastic components in our basically the parts of our tissues that deform and actually give us some energy transfer. So this is the effect. This is in effect where your strength training and maximal force potential come into play. So just after the passive loading of the tissues of the series elastic components, the eccentric muscular contractions start to put the brakes on. So if you think about it, it's really easy to imagine like we're sliding down a hill, right? We're gathering speed, but then we say, let's stop. So we start to dig our heels in and start to gain some traction and eventually come to a stop. So this is where we see massive force being produced to stop the body's mass from falling in its given velocity. So again, you're going down that hill, you've got your body's mass accelerating down the hill, and you've got to start to dig in and ratchet up tension up to a really high level. Once the tensioning has reached its peak, explosive isometric force is employed to cause a change in length of the elastic components rather than the muscle. So once that tension reaches the top, we're not yielding anymore, we're stopping. The muscle traction, the muscle has been achieved, the muscle's locked up, and then the elastic components are what are doing the remaining deformation. And then this is what's ultimately going to contribute to our explosive concentric effort afterwards. This phase is critical for shortening transition time. So when we jump and pop, that's all happening in that pop. Sub 250 milliseconds time period. If it's in change of direction on field of sport, it would be a little longer. But again, we're most of the time trying to shorten that time period. All right, here we are, coupling time. So think about the bottom of our chart, that critical time period where eccentric force effort is stopped, and now we're explosively employing isometric muscular effort, and then we want to get to that shortening and that elastic rebound mixed with our concentric effort. The goal of every strength coach in the world is to shorten this small window of time. That was a typo. This is the transition time between the eccentric to isometric actions and then the start of the concentric. So obviously we don't want to get stuck in the mud and slow down, stop for a long time, wait for the whole play to pass us by, and then come out. We want to be pop, we want to be in and out. This is the moment before we see the contribution of the elastic components. So we've got to really apply the brakes, hit it hard, let those things deform, and then we can basically rip out with the aid of that. That augment the concentric muscular effort. So if you see, the elastic components are not doing everything, but they are augmenting the concentric effort with the reflexive activation of the highest threshold motor units and motor neurons. Our body experiences huge force, and then due to the size of the impulse that we have to employ, it's drawn out of us. It's a reflexive action. So when people talk about it, you can only produce as much force as you can absorb. Fair enough, but we're not going to be able to voluntarily do that by doing a deceleration effort from a snap down or for something like that, right? We're not going to do it by dropping a 12 kilo kettlebell and catching it in a bilateral squat, right? It's something that only the highest threshold stuff comes out when the highest demand comes out, and that means maximal. So this is our critical moment, right? So most actions in sports happen like a relaxed state prior to either touching the floor or another surface that we're not going to move, right? We push on the floor, we move, it doesn't move, or something else, we have to pop off of something else. Anticipation and pre-activation. So before that happens, we come out of the relaxed state, we know we're going to hit the floor, our anticipatory mechanisms turn on, we co-contract around the joint that's going to make contact to stabilize, and then we make contact. and then that traction effort starts to really ratchet up quick because we already have a little bit before we touch. It ratchets up so hard that it actually gets stiff, and then we're at stiffness. Then that tendon can start to rebound and stretch, and bow, then we snap out with the aid of that and our muscular effort, and that is what leads to propulsion in whatever direction it's going to be. So, jumping and field work to train the curve. In the vein of carryover, and we are always concerned with carryover, specific intermuscular coordination is of the utmost importance. Just for a refresher, intramuscular coordination are the internal forces of a muscle, right, and of a particular fiber, and the intermuscular coordinations are going to be your synergistic muscle groups and movers that have a very specific way of interacting in that particular moment for that sport at that speed and that direction, so on and so forth. We can still train intramuscular coordination with nearly identical intermuscular interactions. So think about it. Impulsive loading. I want to train high intramuscular coordination, but with an eye on intermuscular coordination and interactions. So I'm going to run them from 10 yards out at a cone and have them break it down and give me a hard right foot plant on an angle. And I'm going to ask them to stop. They're going to be accepting a lot of force, right? But it's going to be as close as I can possibly get it to what would happen if someone had to break towards the baseline, the ball got hit over the head, and they had to put on the brakes. If we put that in isolation, that would be how we do it. We're training really high, muscles, really high forces within the muscle, but in a nearly identical intermuscular coordination effort. So eccentric force production is very important. That was 3 R's, 3 Y's. Very important, right? This is how we do most things. This is how we start to be able to access our elastic components. With many elastic athletes, the transmission of kinetic energy is their strong suit. So this is what they do well, is redirect this, right? They have really good eccentric rate of force development. They're very good at getting stiff in a hurry. When they get forced into a longer ground interaction, though, or more closed joint angles, it falls apart. So they're only as good as their threshold allows them to be. Right? If it becomes too much, they get broken down. They lose that high open joint angle position. The stiffness gets blown to crap, and then all of a sudden they're like in deeper angles and they're used to, and they're either out of the play or they're on the floor. Deceleration work can do wonders, but just remember that this is strength training work, not quickness work. So if I have someone run, gather a lot of momentum and then run and stop, that this is not working on being quick. This is going to contribute later on, but this is not quickness work. This is strength training work because we are still doing this intramuscular coordination effort work, which is basically strength training. It's how high can I get the internal working forces of that muscle and that fiber. So these are the big ways. All right, stop hard. So if you want to use that hard eccentric training as strength training, be my guest. Teach them to stop hard. That doesn't mean snap downs. Maybe initially you can do things like that, but if you just do little plyometric stuff, it tends to take care of all that on its own. Explosive isometrics at open and closed joint angles. I wouldn't go too deep in the closed joint angle direction, but it's never a bad thing to develop it across a full spectrum. I think we all know that you get more than just that joint angle where we're working the isometric in terms of benefit. It's about 5 to 10 degrees above and below. So it's they have value even at some of the lower angles to some of the angles above. Jumping field work to train the curve. I think this is huge. That's where the impulsive loading comes in, and learning how to manipulate jump height, speed, into movements, angles of the cut. You can manipulate the steepness of a cut or the steepness in and out of a cut to give them a harder force to have to kind of experience and to still perform the same task in hopefully the same period of time. You can. In my opinion, this is the best way to work and produce a result in this type of athletic endeavor. increasing and decreasing joint angles and then producing force rapidly. So working at different angles and having to produce force rapidly out of them. This doesn't always mean ballistics. It just means being able to initiate in the initial phase, being able to initiate 80% of your total force production ability right away at high and low angles, so that you have some ability in all places. But again, it doesn't mean that you're jumping from super deep angles all the time. It just means that we want to learn to initiate and produce force rapidly. So we want to put it all together. If you do a good job, it'll be pretty hard to tell who's the elastic guy and who's the velocity based guy. We're going to watch 2 videos and you tell me, but I think you'll be surprised. Turn the sound off. So there's Daniel. He's doing a 2-way lateral hurdle hop with a change of direction. And then this is Noah. So to most, and I think maybe even to all, they would look at those videos and say, okay, like who's the elastic guy, who's the or the velocity based guy, and who's not. So Daniel, if you look at this, he's in really deep angles. He takes a little bit longer on the ground, but Daniel is actually the elastic one who is not very strong, and if he gets pulled much below that, he's not going to do too well. And then Noah is the really strong guy who squats 500 pounds and is not terribly fast or doesn't do anything significant velocity wise. And after time training both to do both, they kind of end up looking like they can do really whatever they want. And that's kind of the name of the game. Daniel was an All-American baseball player from Stanford and never really lifted any weights. He was just kind of a natural athlete, but he didn't have too much horsepower. And once he got a little bit, I think he got up to like maybe a 400-pound deadlift in a not too long of a period of time, and then he started to be able to really go crazy. And then we started to blend all that stuff back into jumping, and he was just nasty at basically everything. Noah is a pitcher for the Mets. He is naturally a very strong guy. He's a power guy, but we worked on some of this stuff because the scouting report is that he looks like the Tin Man when he moves, and he can't cover first. And if he actually had good power at bat. He hit several home runs in all seasons that he's played, but he couldn't run the bases. And so he looked like Tin Man when he ran. So I was like, all right, well, he's kind of the opposite. I'm not going to do what he's already great at too much. We definitely did a lot of strength training, but I'm going to make sure that I got him that he can move and he's elastic. And we started with low hurdles and not moving in with any complexity, and then we were able to adjust to some of these more advanced hurdle drills with higher hurdles and greater amplitude. So these are my science snippets. These are just some things to keep in mind when you're doing this stuff. I think this stuff's very important. So it's important to always have a little bit of like a scientific blurb to have in the back of your head to say, yes, I'm correct. So whether attention is placed on maximal strength or explosive strength during different phases, it will certainly have decidedly different influences on rate of force development. So training with short, high rate of force development contractions, placing a substantial emphasis on neural drive and explosiveness, rather than maximal force may work to improve early phase of rate of force development. Explosive muscle strength can be defined as the rate of rise in contractile force at the onset of contraction. This improvement seen with explosive training in the early phase might very well be the most important aspect to maximize in athletics where maximal contractile force is almost never reached. So if we look in the context of ground contact time and coupling time, you don't have that much time to do anything. We're talking, in maximum half of a second. So if it takes us 1 to 2 seconds to reach maximal force, well, we have none of that. So if we can get to 75, 80%, or even greater of our maximal force, or maximal contractile force capability, then we're going to be really, really potent. If we can do that in the eccentric regime and isometric regime, and we're skilled at it, we're going to be really potent. So that's why I always say, look, it's more about the start of the movement or the reversal of direction of the movement rather than exploding up and finishing to the top of the movement when you're in the weight room. And this is also important when it comes to plyometric, when you're working on ground contact times. It's really the coupling time and the time on the floor to get on and off, which is the most important part. So you'll see people always emphasizing the final acceleration and extension, and it's like, all right, yeah, it's very important too. But if we're going to do that, we're going to sprint, we're going to jump with the effort and the emphasis on that, or we're going to do something ballistic where we throw something or something becomes a projectile. So it's important when you look at those things to actually read what it is they're trying to say and how can you implement it and change the style of your lifting. Low resistance. 30 to 40% of 1 rep maximum with high velocity dynamic training potentially causes an earlier recruitment of large motor units, increased rate coding, increased discharge of doublets, improvements in synchronization to some extent, and also changes in sarcoplasmic reticulum kinetics. All of these factors play a vital role in rate of force development. So it's closer to what we would do if we were unloaded. So some of the higher force stuff, where the velocity becomes really low, or the time of turnaround in, say, like a hang clean becomes a little too long, or the extension velocity is a little too slow, just doesn't quite get there. If you get really skilled at those exercises and you start to be able to access 80, 85% in some of those movements, well, then that's actually a little different. But that takes time and it takes skill. So we'll go to what people can generally do pretty well right away. I won't read all of this stuff to you. You can read it on your own, but it's an interesting thing when you read and you think about what we've talked about. So I also want you guys to be able to reference where I'm getting some of this stuff and read it for your own, because I think interpretation of some of this stuff is really important and it's critical to understanding. That's basically it. So last thing I'd tell you is if you could zoom in on this particular paper, this is awesome. So this is Verkhoshansky's daughter, but it's when it comes to breaking down the context of the motor structure of an athlete's sport, and how it applies and where the kind of these things that you think would work don't work. This is a really, really great one. So that's basically it, guys. I hope you really enjoyed this. I really enjoy breaking this stuff down and giving some really well targeted stuff and giving different viewpoints than what may or may not be out there already. So thanks for tuning in. Look forward to doing more of these.